Hello everyone, my name is Mingyue Tang and I am a PhD student at the University of Illinois Urbana-Champaign. Today, I'm excited to present our latest work, ChirpEye, passive sensing and profiling of FMCW readers with a resource-constrained tag. This work was a collaborative effort with Jizheng, Dhruv, and Professor Elahe Soltanaghai. Modern reader technologies have been proved highly effective for sensing in both indoor and outdoor environments. Among them, FMCW readers stand out for smart home applications because of its high resolution and strong sensitivity to small movements. These readers are already used in many everyday scenarios, such as human activity recognition, sleep tracking, and vital sign monitoring, quietly supporting our daily lives. However, as FMCW readers become more common, new challenges present. When several readers operate in the same space using the same parameter, the signal can interference with each other, reducing the sensing accuracy. In addition, there is also a growing privacy concern. Imagine someone placing a hidden reader outside your room. It could monitor your activity without you even realizing it. This is why identifying active readers in the environment and understand their transmission parameters is becoming very important today, both for avoiding interference and for protecting personal privacy. There are some existing methods on radar detection and profiling. Previous work have used the spectrum analyzer to capture the spectrum and analyze the waveform. But given the large bandwidth of typical FMCW readers, we need an expensive, high-end spectrum analyzer with high sampling rate. Another work used another active reader with very low transmitting power for processing. But this limits the solution to only readers of same type of limited band. Some existing approach use eavesdropper detectors. For example, one method injects a weak simulation signal to trigger unintended emissions from readers' receivers to estimate the distance between the detector and the reader. This will fail to work in high-frequency scenarios. None of the existing work can identify the radar waveform and localize the reader under low sampling rate without previous knowledge of operating bands. That's why we want to bring our main research question here. How can we detect, profile, and locate an active FMCW reader using an embedded grid tag so we can deploy them easily and can achieve low-cost FMCW reader identification? To detect and profile an FMCW reader, we first need to understand how it works. FMCW reader transmits a chirp signal whose frequency increases linearly with the time. When the signal reflected from the target, it returns with the delay caused by the travel time. By mixing the received transmitted signals, the reader obtains a constant tone that is called intermediate frequency, whose frequency equals to the bit frequency between the two. Because the chirp slope remains constant, the bit frequency increases linearly with the target distance, allowing the reader to estimate the range from the intermediate frequency. However, things become more challenging when we consider hidden reader whose signal configuration is unknown. In this case, to determine the reader waveform such as the chirp slope, we design a tag that mimics the reader operation but swipes the known and unknowns. Building on this idea, to resolve the delay between two FMCW signals and estimate the unknown slope, we designed a delay line tag inspired by the FMCW reader processing pipeline. In our design, the tag uses two antennas and a fixed delay line, denoted as L. Both antennas receive the incoming signal simultaneously, but the signal from the second antenna passes through the fixed actual delay line L, introduce a known delay. When those two signals are combined at a mixer, the second signal arrives slightly later by amount of proportional to L, which can be easily calculated and used for the slope estimation. With the known delay introduced by the delay line, the unknown reader parameters are determined corresponding to the changes of the measured intermediate frequency. However, in real-world cases, the delay between the two received signals is not caused only by the added delay line. When the relative position of the tag changes, the signal propagation through the air introduces an additional delay that depends on the angle of arrival. Specifically, the angle of arrival related delay depends on the angle of arrival theta and the antenna spacing d of the tag. From the simple geometry, there's an additional delay can expressed by d sine theta. At this point, we can see that the intermediate frequency is influenced by both radial slope s and angle of arrival theta. However, since both slope s and angle of arrival theta are unknown, we cannot directly solve either the radial parameter slope or AOA using only the measured intermediate frequency. Therefore, to jointly estimate the effects of the radial slope and the angle of arrival, we introduce an additional antenna with its own delay line into the tag system. With this design, the tag receives 3 copies of the FMCW signal, each experiencing a different combination of delay line delay and AOA delay. When these 3 signals are mixed together, we obtain a time domain intermediate frequency signal, and showing by the green waveform at the bottom. We process the received signal on the microcontroller and convert the time domain waveform into frequency peaks. By applying FFT over a single chirp period, we can obtain 3 distinct frequency peaks, each corresponding to the signal difference between the 3 antennas. Because we already know the structure of the tag delay lines, if 3 intermediate frequency peaks follow the expected relationship defined by these delay lines, we can conclude that the signal indeed comes from the FMCW radar we aim to detect. As we discussed in previous slides, the intermediate frequency peaks are influenced by both radial angle of arrival and slope, which corresponding to the propagation in the air and in the delay line. Essentially, each frequency component presents an equation with 2 variables of s and theta. So we can solve the 3 equations for 2 variables. By applying a linear solver to those equations, we can jointly estimate both radial slope and its angle of arrival. Finally, although the process seems straightforward, but getting clear intermediate frequency in real world is not trivial. Here's a sample of our received intermediate frequency signal as a tag. If we directly take in FFT on samples of 1 chirp, we can see non-separable peaks. This is due to the short chirp duration and the varying difference between the intermediate frequency, both of which decided by the hidden reader. This is also impossible to direct taking an FFT on all the samples, due to the different starting phases of each chirp. Therefore, we need a way to combine signals from multiple chirps. To solve this, we place samples from each chirp into a column vector and stack multiple chirps into a matrix. Then we apply MUSIC, an algorithm that usually applies for finding an angle of arrival. Since our goal is to estimate the frequency, we define Stirling vector as function of frequency f. The MUSIC spectrum is inversely proportional to the orthogonality of candidate Stirling vectors to the noise subspace. However, the tag also picks up like multipass, which also appearing as peaks in the MUSIC spectrum. This leads to ambiguity in intermediate frequency selection. Therefore, we further propose Spectra-MUSIC, which utilizes also the signal subspace to suppress the multipass and enhance SNR. As shown on the right, and for more details, please refer to our papers due to time limit. To summarize, our system, ChirpEye offers an IoT-grade embedded tag solution for detecting and localizing active FMCW radar without the need for active transmission. It features an FMCW chirp-sensitive low-power tag design and can estimate the tag waveform parameters and direction of the signal using a low sampling rate. In addition, we introduced the noise-resilient frequency super-resolution method that leverage information across multiple chirps, making the extraction of intermediate frequency much more robust to multipass noises. To evaluate our system, we built a prototype of the tag using off-the-shelf components. The tag includes three omnidirectional antennas to receive the FMCW signals, coax cables of different lengths serving as the delay lines, and a combiner and envelope detector structure to mix the signal. We conduct experiments in 3 different environments. Each represents a different level of multipass. The first set of experiments evaluates the FMCW radar detection rate across different distances. We can see the ChirpEye can reliably detect FMCW radar up to 20 meters in line of sight conditions and up to 50 meters in non-line of sight conditions. This range is sufficient for most indoor use cases. Compared to FFT or classical music algorithm, our proposed super resolution approach performs better across all the environments with different level of multipasses. It achieves a median slope estimation error below 5% and a median angle of arrival estimation error below 15 degrees, showing strong robustness and accuracy even in challenging conditions. Our text circuitry isn't tied to a specific radio frequency band because the system only needs kilohertz level of sampling rate. That makes the performance agnostic to the radar carrier frequency and bandwidth. To show this, we tested the tag performance for detecting radar operating across different frequency ranges from sub-6 GHz all the way to the millimeter wave. The only requirement is to choose components that can operate in that band. For takeaways, our paper introduced a hidden radar detection system designed to identify and find active FMCW radars using a low-power passive tag. And it proposed the music-based noise-resilient frequency super-resolution method to extract the bit frequency in realistic environments. And also, it can achieve robust hidden radar parameter and AOA estimation across frequency bands as long as the tag hardware supports the frequency range. Here are our references, and that's all for my today's presentation. Thank you so much for listening. Our code repository is linked below, and feel free to send us an email if you have any question about this paper.